All right, ladies and gentlemen, welcome to our next day of probability. Today's lesson is only kind of a slight step beyond of what our previous one was, because it's kind of important that you know how to get your probabilities with kind of some interesting starting locations. Get out your notes. This is on there. We're going to work through these three examples, and then we'll do some examples from your assignment on the next video. So let's start with our first one. We have this lovely Venn diagram, and it's all colors from a box of Crayola washable paints, I guess. And there's 12 of them. That's important to know. You want to know there's 12 of them, but you can go through and you can count the 12 colors. Remember, things in a circle meet that requirement. These are primary colors, so these three are primary colors. We got colors of the American flag, so these three are colors of the American flag, and there's some overlap between them, right? Blue and red are both primary colors and on the American flag. And then there's some colors outside of those two things. And so what's going on is you're going to get the probability of picking these certain color combinations, assuming you're picking out of the whole 12 washable paints. So first one, probability that it's peach. That's only one of the colors. It's right here out of the 12. And so the probability is 1/12. Probability of the colors in the American flag, well, there's 3 American flag colors out of the 12, which is going to reduce a little bit to be 1/4. And now we need to figure out the probability that it's a primary color and American flag. So you need to look at the colors that meets both requirements, which are the ones in the middle there, which are red and blue. So there's 2 out of the 12, and that again reduces to be 1/6. And then we got one here, probability of pink. Figure out where pink is, and it's not there. So that's 0 out of 12. There's no chance of drawing a pink out of this box because pink's not a color. Ta-da, probability done. We got our next example. This one's in the form of a table. So as we go through this, I'll kind of explain a little bit more so you can kind of see some of the examples. So first one, probability of having chores. Well, in your table, you got the having chores row, and you have to figure out which one of these you want. Well, this doesn't have any other requirements on it. It's just number of chores. These ones have further requirements like having a curfew or not having a curfew. So we're not using those two numbers. We're just going to use the total number of people here who have chores to do, and that's going to be the 18 out of 33. That does reduce a little bit. Both of those are divisible by 3, so you get 6/11. I think I could write well enough. The next one is probability it doesn't have a curfew. So again, this column here, it doesn't mention chores at all, so we're not using those two numbers. We'll just use the 8 here, the total number of people who don't have a curfew. So 8 out of 33, and that does not reduce at all there. So our next one is the probability of having a curfew, hooray, and has chores. So curfew and chores, that box is going to be right here. There are 13 out of the total of 33. And then our next one, we have probability of having chores, doesn't have a curfew. And you need to remember what that symbol means. That means and or both of those things happening. So having chores and doesn't have a curfew will give us this box here. It's going to be the 5 out of the 33. And then the last one, a probability of having a curfew. Well, it doesn't have any other requirements on it. So you're not gonna be using these two boxes because those have the other requirements dealing with chores. Instead, you're gonna use the 25 here to get 25 out of 33. So hopefully that's kind of helping you, 1, get probabilities again, remember what these symbols mean, what and means, and 2, be able to read these tables and understand them a little bit better. So we're gonna have one final example from your notes. And this is the part that has something new. And it's this tiny part. Sorry, I really should have made this bigger, really should have highlighted it more. But this is kind of the idea behind this lesson and why you're having it. 2 events are quote-unquote independent if, well, you got your little formula. Probability A times probability B is the same thing as the probability of A and B. What that basically means is one event does not affect the other. So, for instance, if you're rolling a standard die and you're flipping a coin, those are going to be independent events, right? When you roll the die, it's not going to change the probability that the coin's going to land on tails or heads. Those are independent events. In fact, rolling a single die can be independent events if you do multiple rolls, right? You roll a die, it ends up 3. You roll a die again, it can end up 3 again. It can end up being 6. The probability of the second roll does not depend on the first one. And so those are independent events. So what's going on is you'll be given like a lot of tables, Venn diagrams, and you need to figure out if the events there are independent. And the way to calculate if they're independent is this. Because these numbers here are kind of a mess. It's really hard to tell, like, if someone's in 10th grade, does that mean they're more likely to be male versus if they're in 12th grade, they're more likely to be male or not? And so there's some question of independence there. Well, we can look at this, right? Are being male and being in 10th grade independent? That's the example I was just talking about. Well, if you're going to do that, you got to figure out the probability of male, and you got to times it by the probability of being in 10th grade, and you need to figure out if that is the same thing of being a male and in 10th grade. Okay, so you got 3 probabilities you need to calculate, and you need to figure out if this equation is true. So we got probability of male. Well, there's 832 of them out of the 1,571, which is kind of a lot, but that's okay. We're just going to write out our little fractions here. It won't be needed to times that by number of 10th grade, or probability of being in 10th grade out of the 1,571 there. So we got 605 10th graders out of the 1,571. And we need to figure out if that's the same as the probability of being male and in 10th grade out of the total there. So that's 320 out of 1,571. This is where calculators come in very handy. Go ahead and compute this and compute this. Just turn them both into decimals and figure out if they are the same or not. So go ahead and pause the video and calculate those. Alright, so you should have gotten, if you round it to your third decimal place, you get 0.204 for both sides. And that, since those are equal to each other, that would be yes, they are independent. Let's write that down. Independent. I think I could spell. But there's one small thing I wanted to mention about this. If you look at your non-rounded decimals, which should have been things like this, they're not exactly the same. Right, you got 0.2039, 0.2036. And that kind of brings into questions like, what decimal do you round to? Like, how close do they have to be for them to be independent? Well, for our purposes here, let's say within 1%, then we'll say they're independent of each other. Like this is a matter of 0.3%, so those are pretty close to each other, even less than 0.3%. And so even though they're not exactly the same, if they're really close, then yeah, we're going to say they're independent of each other, or like fairly independent of each other. Kind of as these two numbers differ, right, one becomes quite a bit different than the other, then we'll say these are not independent anymore. And so let's have you try out this next one. You're still computing the same idea here. You're trying to figure out if female and being in 12th grade are independent. You can get probability of female, probability of 12th grade, and get probability of being female and in 12th grade, and see if those you get a true equation or not. So go ahead and pause the video and figure it out. All right, let's have you check and see. On the left side, you should have gotten 0.129, and on the right side, you should have gotten 0.137. That is not within the 1% there, and so we're going to say no, not independent. And there you go. independent. Independent. Yeah, that's the actual word, not independent. That sounds like it should be a word. Anyway, so yeah, if you got that, congratulations. No, they're not independent because they're not that close. These close. These not so much. And so there you go.